Welcome back. This is part B of Concept PTO 11.5 alternating series. Earlier in part A, we saw how we test an alternating series by alternating series test, and the requirements are the positive terms of the alternating series. Bn plus 1 is less than or equal to Bn, or the sequence Bn is decreasing. What is the relation between Bn and An? An is the given nth term of the given alternating series. And if you take the positive part of An, that becomes Bn. So Bn are all the terms of the sequence Bn are positive. Then you are going to first show that it is a decreasing sequence and then the limit of the nth term equal to 0. As I said earlier, it's not always in this order you should do. You can also do sometimes the second condition first and then the first condition. The reason being the second condition is easy to prove. The first condition sometimes can be harder, where we have to show decreasing by considering a relating function and doing the decreasing test for the relating function. So this is what we did in the earlier one, and then now we'll try example number 2. Is the series -1 to the power n3n divided by 4n minus 1 convergent or divergent? Justify. So always we take without the sigma sign, the given in the given series, this without the sigma as the nth term of the series. So, because of the presence of -1 to the power n minus n in the problem, so you see -1 to the power n because of this presence. So it is making the term negative, positive like that. It changes alternatively negative and positive, starting with negative. So that -1 to the power n tells that the given series is an alternating series. It's an alternating series. So obviously you would go for alternating series test. So it has got two conditions. Now in this problem, let's try condition 2 first. Condition 2. What is that? Limit as n approaching infinity of Bn. What is Bn? Bn stands for the numerical value of the positive part of An. The limit as n approaching infinity Bn is limit as n approaching infinity. In the An, you remove -1 to the power n, which is what associating the sign, positive or negative. So without the sign, it becomes positive. It's 3n over 4n minus 1. So when both have n in it, the best way to do this, to directly apply infinity for n, it is infinity over infinity type, which is indeterminate. So we are going to divide this by n, this also by n. You can also divide by 4n. So now it becomes 3n over n, which is equal to 3. Then 4n over n, that will be a 4, minus 1 over n. This 1 over n part becomes 0 because it's 1 over a large number. N is approaching infinity. So this will be, so this value is equal to 3 by 4. The limit is n approaching infinity, Bn is not 0. So condition 2 fails. Condition 2 fails. Also, if you consider limit as n approaching infinity of An, in fact, we are actually considering the test for divergence in this case. Limit is n approaching infinity of An. is limit as n approaching infinity of -1 to the power n bn, right? So the only difference between an and bn is that -1 to the power n part, which associates the sign. So this becomes plus or minus 3 by 4. So this means that limit um, n approaching infinity of an does not exist. Does not exist because it is plus 3. It oscillates between 3 and 4. So it does not exist. Therefore, you can either use alternating series test, alternating series says that condition 2 fails. Um, that means this series is not convergent, or because of the second condition failing, you can also say that test for divergence says that the limit does not exist. If it was not equal to 0, then you can conclude that it is divergent, right? So you can say the given series, so the series diverges by the test for divergence. Which is an alternating series, -1 to the power n times 3n over 4n minus 1 diverges by test for divergence. Let's try example 3. Test the series sigma -1 to the power n plus 1 times n square over n cube plus 1 for convergence or divergence. So obviously, because of this -1 to the power anything, this makes it, so this will be a plus or minus. So when you plug in n equal to 1, it's going to start up with a plus sign, and then it alternates plus or minus 1, plus 1 or minus 1. Okay? So that makes it an alternating series. The series is an alternating series. Because the series is an alternating series, you would apply alternating series test. The given series is an alternating series. So apply alternating series test. So we have to prove first condition bn plus 1 less than or equal to bn. And then second condition limit of bn equal to 0. So let's establish condition 1. That is to prove bn plus 1, which are the positive parts of sigma an, bn plus 1 less than or equal to bn for every n. That's what we have to establish. So what is bn in the problem? Bn is absolute value of an, which is n square without the -1 to the power n plus 1 part, n square over n cube plus 1. So is this sequence decreasing? Is this sequence decreasing? In one of the earlier problems, we were able to prove this decreasing condition very easily. In here, in this one, we just compared bn plus 1 and bn because the numerator was just a constant 1. The numerator was just a constant here. So such a comparison was very easy. In this case, the numerator is a polynomial in n. So it's better we use a relating function and consider the relating decreasing test for that function. Consider the relating function f of x equal to x square over x cube plus 1. Always when you do the relating function, change the n to x. So is this function decreasing is the question. So find out the derivative, apply decreasing test or increasing decreasing test. For that, you will apply the quotient rule for the derivative. So it is denominator times derivative of numerator minus numerator times derivative of denominator divided by denominator square. Just 2x to the power 4, 2x to the power 4 plus 2x minus 3x to the power 4 divided by x square plus 1 the whole square. So f prime x would be, if you combine the like terms, it is 2x minus x to the power 4 divided by x square plus 1 the whole square. So if I common factor the x, it's 2 minus x cubed divided by x square plus 1 the whole square. The denominator is always positive because it's a square. Denominator is a perfect square, so it is. So f prime x, we have to show that it is decreasing. That means f prime x should be proved to be less than 0 eventually. So the sign of f prime x is only depending on the sign of f prime x is the sign of the numerator. So x times 2 minus x cubed. In the context of the problem, this x is positive because the context is all n more than 1, 1 or more than 1, greater than or equal to 1. So x is always positive. So 2f prime x, the value, the sign of f prime x will be less than 0 if 2 minus x cube will be less than 0. When 2 minus x cube is less than 0. Or when x cube is more than 2. Or when x is more than cube root of 2. So whenever x is more than, because we are talking about integers in the problem, because the series is n equal to 1, n equal to 2, n equal to 3, and so on. Even though x can be a value between two integers, but n cannot. In the context of the problem, we have to take x to be an integer. So it's x is more than cube root of 2, means whenever x is more than 2, it is going to be f prime x is less than 0. So we can say f of x is decreasing on the interval whenever x is more than or equal to 2. Or we can say sequence Bn is decreasing for n more than or equal to 2. So what is condition 1 that we have proved? Bn plus 1 is less than or equal to Bn for n more than or equal to 2, which is okay. We don't have to do right from 1. Eventually, it is decreasing. So what is condition 2? This limit as n approaching infinity of Bn, this should be equal to 0. So let's see whether it is true. Limit is n approaching infinity of Bn. Bn is the positive part of An. It is n squared by n cube plus 1. So if you divide the numerator and the denominator by highest exponent of the denominator, which is n cube, divide by n cube, divide by n cube, you get this to be limit n approaching infinity, 1 over n on the numerator, denominator is 1 plus 1 over n cube. So we get this to be 0, even this to be 0. So it's 0 over 1, which is equal to 0. So condition 2 is also proved. So condition 1 is proved. Condition 1 is proved. Condition 2 of alternating series test is also proved. So putting these together, we can conclude by alternating series test, sigma an is a given series, just sigma -1 to the power n plus 1 times n square over n cube plus 1 is convergent. Note, while proving condition 1 of the test, which is the decreasing condition, sometimes you need to consider the relating function f of x, which is what we did in this problem. So when will you choose the relating function? When the numerator is not a constant. And if it is a polynomial in n, then you would choose the relating function. So you will have to refer to the section videos for problem number 5, 11, and also I have done one more problem, number 13, in the section videos. Please refer to those. Hope this video helps.